under what type of conditions we need to consider this vacancy concentration, which means that we need to consider the vacancy mediated effect under we have a temperature or thermal gradient acting on our materials. So we will address this. The title here will be when must the vacancy concentration be taken into account? So there are two typical cases here. The first one is in thermodynamics, when the vacancy concentration or a fraction of vacancy is around 10 to -3 to -4, then you cannot ignore the vacancy effect or vacancy mediated effect. Or in kinetics point of view, the heat of transport or vacancy formation energy, heat of transport is close to vacancy formation energy, or you do have a large temperature gradient. Under this situation, you still cannot ignore the vacancy mediated effect under you have a thermal gradient or temperature gradient acting on your materials. So I'm going to give you some examples here. What we have here is we have a copper, nickel, alumina, and silicon with its corresponding crystal structure. We have FCC, BCC, and diamond cubic for silicon. And as you learn, you have probably some of you have known that for copper, nickel, and aluminum, most of this material, the vacancy formation energy is around 1 eV. But under atmosphere room temperature, and the vacancy fractions is ranging from 10 to -23 for the copper, 10 to -25 for nickel. For alumina is larger, is 10 to -12. But however, actually it's quite small. And you don't need to, if you move to like a silicon, it's even smaller. Is 10 to -16. But when you try to increase the temperature up to 1000 K, and which means that it actually can be considered as we do have the one side, if we increase the temperature, we probably you have a can be equal or means that probably you have a large temperature gradient. When you increase temperature up to 1000 K, you can visualize the copper the vacancy fraction can dramatically increase up to 10 to -4, -5, -3. Okay, so actually, when you just simply increase the temperature up to 1000 K, which means that around 700 degrees C, then you can visualize the vacancy concentration significant increase. So under these situations, you cannot ignore the vacancy mediated effect. Okay, so I'm giving you some like a short summary here for high temperature metals, as long as atomic fraction go up or increase to 10 to -3 to 4, you cannot ignore vacancy concentration. Or for some metals with lower melting point, for example, like alumina, lead, and tin, their vacancy formation energy is quite small, which means that easy to have a vacancy, to form a vacancies. And in this type of materials, you still cannot ignore the vacancy concentration. So give you a quick summary here. When you have a thermal gradient or temperature gradient acting on your materials, and as long as this is large enough to drive atomic transport, and depending on different material systems, we can easily formulate the atomic flux driven like this, driven by the chemical potential gradient or fixed First law, and the second term is due to the thermal migration, will be the mobility concentration and the driving force. And for the pure metal, or some people call it as a vacancy mediated materials, you need to consider exact thermal migration induced atomic flux, which is the mobility concentration and driving force. But you still need to consider the vacancy mediated effect, which can be addressed here. So give you a quick summary for thermal migration. What's a thermal migration? Actually, it's a cross effect between the diffusing species and the heat flow. And we can design an experiments to quantitatively analyze the magnitude and also the sign of heat of transport. And the sign of heat of transport can tell you how the diffusing species moves. Is from high temperature move to low temperature, which corresponding to positive heat of transport, or this diffusing species moves from low temperature toward to high temperature, which is we call have a negative heat of transport. So the sign of the heat of transport can determine the directions of the atomic flux induced by thermal migration. And this is just for your reference, okay? But next, I'm going to highlight or ask you some questions the thermal, uh, regarding to the thermal migration. And this is some practical case always happen when uh, you are designing the solder bond in your chip. If As you know, the solder bond or solder joint actually is bind the silicon substrate to copper substrate. But under this situation, if my question is, how can I determine the heat of transport for inside this material is positive or negative? So the question is how to determine whether thermal migration really happens in your solder bond. And the solder bond actually is here, which is bind the silicon substrate to copper substrate. So probably you will answer as we just the prior slide or this slide demonstrate that you can just put two solder bond which are not really which this solder bond only suffer temperature gradient but do not have current passing through this material. So by analyze the element or component or atomic distribution along the solder bond or inside the solder bond, you can make sure whether the thermal migration really happens under this specific temperature gradient, right? So yes, this can answer the question one. But the other question would be, but how to determine the heat of transport is positive or negative? You can, as I mentioned, you can visualize the um, the atomic distribution, atoms distribution before. You can compare the atomic distribution before and after you acting the temperature or you apply a temperature gradient across these materials or this solder bond. Yes, so you can you can design this type of experiment to answer both these questions. If you observe the distribution atomic, or you can visualize the atomic migration, which means that thermal migration really happens. And by further analyze where this atoms moves, then you can determine the heat of transport for this lead is positive or negative. In this case, the lead actually, or the tin actually moves from low temperature side at the bottom moves to second side with a higher temperature, and the heat of transport for sure is negative. But further, some people probably will ask further questions. Professor, let's two solder bond. There are only temperature gradient acting on these materials, but serving as a real solder bond actually is also electrical supporter or connection as well. So which means that there should be a current passing through the solder bond. And also in the meantime, should have a temperature gradient acting on these materials. So serving as a real solder bond, actually they are current passing through, and also it will suffer temperature gradient. Under these real situations, are there any a method or any strategies to determine what's the real heat of transport for the atoms here? So the question here would be if I have the pure tin serving as a solder bond, and also this solder bond now is a functional solder bond, which means that you do have a current passing through it, and also accompanied with a temperature gradient acting on it. Under these situations, can you design an experiments to measure the heat of transport for the tin? So the information I given to you here is the pure tin as a functional solder bond, and after 16 hours, the current densities is shown like this. So this solder bond, we can observe the current passing through it from downward, and also the secant size here. So we do have a high temperature at the upper and lower temperature at the bottom. And after a while, you also can visualize the large void across the upper region. So are there any way to answer or measure or tell you the heat of transport for this tin atoms? Any ideas here? How to design experiments to answer this kind of situation? You do have two possible driving forces. The first one is electrons flow, and the second one is temperature gradient. It's our both driving force. But we want to know the heat of the sign for the heat of transport. So you can imagine that if the heat of transport for the tin is positive, then this sorry, probably I can, because animation is like this. So because for the pictures, electron migration, actually the direction is moved downward, and you visualize the large void, right? Which means that probably the EM happens. The atomic flux for the tin induced by electron migration is the same, moving the same direction with electrons. So I have the atomic flux move downward, right? But in the meantime, I also suffer the thermal migration, but I have no idea. The heat of transfer is positive. If it is positive, the atomic flux will be induced by Tm will be go downward. But if negative, which means that atomic flux will be moves from low temperature toward to high temperature, will be upside directions, depending on the sign for the heat of transport. So only two possibilities, either this way or this way, right? So in order to know which way, which directions of the atomic flow induced by Tm, so probably I can do one this design is no matter is this way, atomic flux induced by Tm is this way or this way, it's not going to change when I switch the direction of electrons flow. So when I try to switch the directions of electron flow to go upward, which means that the atomic flux induced by EM will be go upward. And after 6 hours, I can also visualize, uh, cut into a side view or cross section and 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 get this SEM images. Then I visualize the void gas motor. You have a large void at in your left-handed side, but a small void in your right-handed side. What happened? Which means that even though you switch the direction of electrons flow, but the atomic flux induced by thermal migration is the direction for that is not going to change. So I can figure out or find out that the atomic flux driven by thermal migration for sure will be moved downward. Why? Because I have this plus this, so void get larger, and this plus this gas molder is makes sense, right? So I can make a gas, and almost I can confirm that the atomic flux driven by thermal migration is moved downward, which is moves from high temperature toward to low temperature, which also show that the heat of transport is positive. Some people probably will have like some people probably were curious about, yes, Professor, how can you get these results? Because don't forget that for the silicon side, always higher temperature and low temperature at the bottom. So the heat of transport, only the atomic flux driven by heat of transport for sure, just one directions, is not going to change. Even though you switch the direction of electrons flow, it's not going to change, right? Because the high temperature is due to the light width. Higher temperature because the silicon side have a smaller light width compared to copper side, responsible for heat dissipation. 所以在这里的话，你可以简单的透过你翻转你的电流的方向，因为其实thermal migration induced atomic flux，不管是往下或往上，它不会因为你旋转你改变电子流的方向而改变。因为在 silicon side 这里的线宽是比较小的，那它 current density 就比较大。那根据欧姆定律的话，这边会比较热，那这边会因为 current density 比较大。然后低温的话，这边就是因为它的线宽比较大，那它的温度会比较低，所以才会有一个 temperature gradient。所以从这里的话，你就可以知道，我如果简单翻转的话，那我就可以确认一下，我就可以知道说，这刚好就是比较大嘛，然后它们两个相反，它刚好比较小，所以就可以 confirm 我的 atomic flux induced by Tm 到底是哪个方向，给大家做参考。Now, I'm going to give you a quick summary for EM and TM. Electron migration is the close effect between the diffusing species and electrons flow through the momentum exchange. And you also can design an experiment to quantitatively analyze the sign and also the value for effective charge beta. And are there any, because EM actually is unavoidable, you cannot avoid the EM happens as long as when uh, the light width for the conducting line dramatically decrease, so the current density dramatically increase. Under these situations, EM effect is unavoidable. So, what are there any possible driving force can counterbalance this EM-induced atomic flux? Yes, fixed burst law and also the stress gradient, which we call a batch effect, can try to counterbalance this effect. And stress gradient, don't forget, this is related to material property because when the metal is suffering some tiny external driving force, to lead it have some strength still within the elastic uh, deformation regime. And under this situation, we are not going to get any permanent distortion or deformation. But when the external driving force larger than yield strength, not yield strength, it's not that we call it's yield strength, then uh, then the strength oh, okay, the stress is larger than yield stress, then under that situations, then that will lead the you will get a larger strain, and which will lead the plastic deformation. So I'm going to grab some figures to show you. So it's here. So as long as the stress larger than yield strength, then you will get larger strain, which reach the plastic deformation region. Then that will, which means that you will cause the extrusion and also void formation. So this is the one we just mentioned. Stress field actually can counterbalance this EM flux. And the others we just addressed. One is thermal migration. It's a cross effect between the diffusing species and heat flow. And you also can design experiments to quantitatively analyze the sign and also the magnitude of heat of transport. And as we mentioned, or as the case we just show you, actually the thermal migration is not also unavoidable. So are there any possible driving force can counterbalance this effect? Yes. The one we just mentioned is the concentration gradient, which is fixed first law. Okay. And I want to address here. So there are other possible driving force to counterbalance um, the EM. Some people will design them as a case I just show you here. So you can also allow the you also can allow the atomic flux driven by TM to counterbalance the EM as long as this um, they do have upside uh, moving directions, but same magnitude. So this EM can counterbalance this atomic flux driven by TM can counterbalance the atomic flux driven by EM. So this is, and also the EM probably can also can counterbalance the TM. So far, I have read lots of recent articles. So the new design idea for solder bond actually is just allow unavoidable atomic flux driven by EM equals to TM. So then you have chance to get the flux of for in quincy steady state equals to 0. So you can get so you can avoid all this void, I mean TM in or EM induced void happen or observe in your solder bond. So just for your reference，所以从这里就可以发觉到说，在线宽越来越小的这个时代里面，current density，因为你要放更多的 chip，所以你的 current density 绝对是往上拉的。那绝对是往上拉的情况之下，大家可以预期 TM 跟 EM 所 induced 的 atomic flux 是 unavoidable，就是不可避免的。那在这种情况之下，既然他们不可避免，你可以预期他们很大的情况之下，fixed first law 其实已经很难再抵挡它了。但如果你就这样子让它无止境的发生，那你可以预想得到你的 chip 的 reliability 就会下降非常非常的多。那这也是我们不期待的，我们总希望我们的手机可以用很久。那是不是有机会找到这个材料它的yield strength 事实上是很大的，那它就也可以来 balance 我的 EM。但其实每个材料它的 yield strength 它的 elastic region 其实基本上是受限于这个材料的当初它的 composition 跟组成。所以后来比较新的设计收得棒的 idea 就会是，我们是不是有机会让两个都无法不发生的 EM 跟 TM，让它们的方向相反，然后值相等的情况之下，是不是就可以达到quincy steady state，就 net flux，就是 atomic net flux 事实上 equals to 0。那这样的情况之下，我是不是就可以 make sure 我的这个 solder bond 它不产生 void formation，不会 extrusion？ 那这就是目前比较新在solder bond design 的这个 idea，给大家做参考。Okay, so let's move to the fourth section we call the capillarity effect. Capillarity effect, as we mentioned before, it is curvature-dependent surface chemical potential. What this means actually is we do have, as long as we have a curvature-dependent surface, which means that we have a curve surface, and this will induce the atoms have a different surface chemical potential, and this different surface chemical potential will drive atomic transport. This is we call a capillarity effect. So the purpose here is also the system always turn to or move to minimize total free energy of the system. So surface evolution driven by minimization of surface chemical potential. So I'm going to give you an example here. So due to the atoms have different surface potential, or the atoms do have the surface potential gradient, then that induce atomic transport. So we call a capillarity effect. So what we have is instead of have a flat surface, now we have a curved surface showing blue. And the surface potential, what the surface potential means? When the atoms at the interface in between the gas and also the solid interface, then it will have a is have a surface potential. And this potential will depends on the local interface curvature, kappa. And we do have, because it's curve surface, right? We have two kappa, kappa 1 and kappa 2. And the curvature actually is a reciprocal of radius, R1, 1 divided by R1, or 1 divided by R2 is a reciprocal of radius. And why we do have two? Because it is curved surface. So usually we have two orthogonal axes to represent this curved surface. So we have kappa 1 and kappa 2。所以我们两个正交轴来描述任何一个曲面，所以因此我们需要两个正交的轴来描述这个曲面，所以你就会有两个轴，所以它们就会相对应会有两个半径，那就会半径分之一就会是 kappa 1跟 kappa 2。So what exactly the surface potential be expressed? If I have atoms at this we call a convex region, 就是凸的地方, then its surface potential can be written as mu A0, means that the chemical potential of atom A on the flat surface in pure A materials. So we call it mu A0. And now it's not at the flat surface, so we need to plus the extra term. This term is correlated with or related with its curvature. So we have a gamma is a surface energy times the average atomic volume, or you need to times kappa 1 plus kappa 2. So the kappa also, as we mentioned, is a reciprocal of radius. So this is the surface potential of atom A. And we use this to make sure this is the positive term. But however, if the atoms now at here, which we call a concave region, 就是凹的地方, but also the surface potential can be written as here, but the difference part is minus. So at the convex region, the chemical potential of atom A at convex region is larger than that on the flat surface because you plus the extra term, and this is positive. So for sure, this term is larger than the chemical potential of atom A at on the flat surface. But however, if the atom now is at the concave region, we use a negative or minus a positive term, which means that this value of its surface potential for sure will be smaller than it on the flat surface. So now you have the surface potential difference. So this gradient divided by distance, the difference of gradient will drive the atomic flux. And from where to where? Usually will be from high surface potential side, move to low surface potential side. So the atomic flux will be moved from here, convex region, move to concave region. So the system finally will reach planization. So this is why if you have a curved surface, finally it will tend to become the surface planization，就是平坦化，最终会达到一个平面。So this is the atom point of view. So if it is a vacancy flux, vacancy point of view, the moving direction will be go upside direction. So this is for reference. But as I mentioned, how the atoms move from convex region to concave region is through, probably or through interstitial side or exchange with vacancies. We will talk this in lecture 4. The detail how this atoms moves through convex region to concave region, we will discuss that in lecture 4, okay? So this is what we call a surface planization or surface moving through this capillarity effect. But now some people probably will have some questions come out from your mind. Professor, why the atoms at convex region have higher surface potential? Can you prove that? 为什么在凸的地方它的能量比较高？老师，你可以再说多一点吗？为什么？这是要背起来的吗？还是有什么特别原因？In order to persuade you, so I'm going to use one slide. Actually, your textbook use like 3 slides to show you actually the atoms at convex region have higher surface potential compared to at the concave region. Okay, so I'm going to show you why. So we were starting from the atoms, the surface chemical potential on the flat surface. Okay, and also what type of material we discuss with? We have a pure metal A, but with a vacancy. And at constant temperature and no electrical field. So write it down. If I say no electrical field, which means that no EM. At constant temperature, which means that no TM happens. Okay. So what we have here is we have pure A with vacancy. Okay. So under this situation, can you just roughly write down what's the chemical potential of atom A on this flat surface? And also what's the mu V? So because we only have 2 components, atom A and vacancy, so the total Gibbs free energy can be written as mu A Na numbers of atom A times its chemical potential plus numbers of vacancy times its Gibbs free Gibbs vacancy formation energy and times KT Na ln XA and NV ln XV. This is we have told you before. And due to, as we mentioned, that chemical potential of atom A actually is when you added 1 moles of atom A, the changes in total Gibbs free energy, we call the chemical potential of atom A. So we directly use Gibbs free energy partial with Na. So we only have this term, and we don't have this term because this term don't have the Na, right? So we have this term and also have this term. So we got the partial with this term. So KT this term, and this term is nothing related with Na. So we find this result. Mu A equals to mu A0 plus KT ln XA. But as we know, the vacancy number is much smaller than the atoms. So we can delete this term. So we got the mu A equals to mu A0. under these situations due to NA much larger than NV. But how about NV? So probably you will write the same thing. You just mu V equals to, you need to partial this term with NV, right? So you got this term, vacancy gives vacancy formation energy, and also this term. So we got the KT ln XV. So we just write this down. Okay, so now you have the mu A equals to mu A 0. Then mu V equals like this. It gives vacancy formation energy times KT ln XV. Okay, so now we make a very important assumptions here at local equilibrium condition at service. What this means that the local equilibrium at service, so which also show you that the chemical potential of a vacancy equals to constant, equals to 0 here under equilibrium condition. This assumption is quite important because this can help you to get what's the exactly atomic fraction for vacancy. So when you have a constant chemical potential of vacancy under these situations, local equilibrium service, which means that every vacancy on the surface have the constant chemical potential, which also imply you that we don't have vacancy flux, we don't have chemical potential variation. So which also tell you that there's no flux. So why this makes sense? So under this situation, we put it back. So we label with equilibrium, so equals to 0, equilibrium here. So based on this equals to 0, so we can get what's the XV here. Just move to this to here and divide it by KT, so we can get the XV. Show like this: exponential negative vacancy formation energy divide Gibbs free energy divided by KT. So this is how, this is actually you know this results, right? So how to derive here is starting from here. So I have shown you on the flat surface, the vacancy fraction can be expressed like exponential negative Gibbs free the vacancy gives free energy for vacancy formation and divided by KT. Vacancy formation gives free energy divided by KT. So when, as you learn, when you increase the temperature, which means that you got a smaller, this value negative smaller, so which means that you have larger atomic fraction for the vacancy. So we have more vacancy as long as you increase the temperature. So this is what you have learned, right? But all this is at the flat surface. So vacancy formation gives free energy on the flat surface. Do you think this will be the same as at curved surface? Do you think they are the same? No, right? So as long as we're talking about at curved surface, because this is on flat surface, when you want to form a vacancy, how much energy you need to end it. But now the system moved to the curved surface. So it turns out you need to ended the vacancy on the curved surface. So which means that you probably need to add in more energy or put more energy to push the vacancy on the surface, form on the curved surface, right? So it turns out if the system, instead of the flat surface, now it's curved surface, you need to modify this term. Then that will help you to know the atomic fraction of the vacancy on the curved surface. Why this is so important? Because we need to answer to want to persuade you what happened on the curved surface. So in order to get this term, vacancy formation gives free energy on the curved surface. So let's move to let's step by step, okay? Now what we have, instead of the flat surface, we have a curvature dependent surface here. And how to get the curvature-dependent surface potential? So you can get this image, you can image this system. We have a sphere with a radius r. Now I want to put ended vacancy on the surface, on the surface of this sphere. And as long as I ended the vacancy, or instead of ending a vacancy, it's difficult to image that. So probably you can think that I ended the lattice point on the surface of the sphere. And that probably will increase the radius of the sphere. And also, so that will increase by delta r. Okay, and this curvature will be the reciprocal of this radius. And kappa, as I mentioned, kappa is kappa 1 plus kappa 2. And if this is sphere, which means that uh, kappa 1 equals to kappa 2. So we will get 2 divided by r, because 1 divided by r plus 1 divided by r, you will get 2 divided by r. And as I mentioned, when I ended the lattice point on the surface of the sphere, then the volume, not only will you have the increase in radius, probably will also will increase the volume and also the surface area of the sphere. So the crystal span by delta V will be equals to omega V. Omega V will be equals to omega A, and also you have the increased surface area by delta A. Okay, so in due to you have, because actually I'm more interested in how much energy, extra energy I need to create the vacancy on the curved surface, how much extra work I need to perform, right? So I need to know how much energy be increased when I ending a lattice point on the surface of this sphere. So the energy point of view, so that will be due to we have increased surface area. So as long as when you when you need to know the service work, how much service work be increased, then you use the area. So we have the gamma, which is service energy, you times the increased service delta A. So you know the service work be increased by gamma delta A. But I still have difficulty to link delta A, the increased area, with the omega V, because I know that this is every atomic volume, right? But I have no idea the delta A. So are there any relationship between delta B and delta A? So I got the relationship. The delta A can be shown as a 8 pi r dr, and the delta V can be written as a 4 pi r squared dr. So you use this delta A to divide it by delta V, then you got a 2 divided by r, and this is kappa. So you got the delta A can be expressed as a kappa times delta V, and we know the delta V equals to omega V. So I can substitute gamma kappa omega V here. So the extra work I need to this is just for your reference. So as long as you deal with the sphere, then you got kappa equals to how it's y equals to 2 divided by r. But here, if you have a curved surface, the extra work you need to perform here or added to the system would be gamma kappa omega v. So back to this, actually you need to add extra gamma kappa omega v. So after gamma kappa omega v, so we can rewritten the vacancy, the atomic fraction, or the vacancy fractions under equilibrium conditions at curved surface. Kappa as a function of kappa can be written as exponential negative vacancy formation gives free energy divided by kT, and the modified term is delta the increased work, right? Actually, it's a gamma, kappa, omega v. You can substitute here. So these results can be written as this is flat surface because kappa, when kappa equals to 0, which means that you have the radius is infinity. Reciprocal of infinity, you got 0, right? So you can, this is flat surface, and you have this term is negative, you put here, negative gamma kappa omega v divided by kt. Oh, so you can rewritten as here, you just put it at the bottom, so you got this results. So put back. So instead of the flat surface, if what is flat surface means that kappa equals to 0. So exponential 0 is 1, right? So kappa equals to 0 means the flat surface, you got the concentration of vacancy show like this. But if not kappa is not equals to 0, so you can rewritten, you can get this relationship, can help you to know the concentration of vacancy in terms of kappa. Okay, so now we have chance to know the atomic fraction of vacancy on the curved surface, like this, show like this, or this. So this is for vacancy. But how about if I, instead of ending a vacancy on the on the crystal or on the curved surface, how about I ending an atom? So I just substitute V as A, right? So the extra work also I need to perform, or I need to put into the system will be also gamma kappa omega A. And as you know, gamma omega V equals to omega A, right? So the surface chemical potential for the atom can be also written as a phi AS on the surface and will be mu A, right? Chemical potential of atom A. And as I mentioned, in this system, we only have the vacancy, so the surface chemical potential will be will be expressed as mu A minus mu V. And as we know, we always, under equilibrium, local equilibrium condition, we always allow, assume mu A equals to 0. And sorry, mu V equals to 0. And mu A can be shown as mu A 0 plus delta work. So here, due to here, so we got the atoms at the curved surface express mu A 0 plus gamma kappa omega A. And here, the kappa is positive. So this is how I successfully to prove that why the surface potential of atom A can be shown as here. And as we mentioned, in the convex region, kappa is positive, and for concave region, it's negative. Kappa can be considered as negative, so you have a higher surface potential at concave region compared to concave region. So, but it is not easy, it's easy to remember due to you ended something on the surface. This curved surface is convex region, right? You need to use energy to push or to put this lattice point on this sphere. So for sure, you deliver energy to the system. So this system, these atoms have higher energy on the concave region. 所以在这里，其实，我们主要是透过先证实给同学们看说，如果我是放一个 vacancy 在这个曲面上的话，那我要给这个系统多少能量？不管是你是放一个 lattice point，或者是一个原子，它都需要给系统能量，才有办法把它塞在曲面上。所以第一件事情就知道，你做功把这个东西，把这个原子塞在那里，那这个原子就拥有比较高的能量。所以在凸出来的地方，一定能量都会比凹下去的地方还要再高，这样就可以比较容易记得。所以它这里一定会是正的，伽马卡跑欧伽 A。但反过来，如果是凹的，那你就可以想它就会是比较低，所以就可以用减的，所以这样就比较容易，这样比较不会记错。 So now you have the gradient, right? So the driving force is negative chemical potential, is a potential gradient. So we have a gamma omega. Gamma omega is constant. So the only one you have gradient term actually is you have kappa gradient. So we have a negative kappa gradient for atoms. For atoms also, and if some people want to express, show them in terms of vacancy, we have upside sign, so it will be for the vacancy. So, but this is just for your reference. Due to atoms can active moves, but vacancy is not, right? The really move, it really moves. I mean, the really moves subject in materials are atoms, not vacancy。就是在材料里面，不要忘记，就是 vacancy 其实不会主动移动，真正移动的是原子，然后它会给你一个错觉，说是 vacancy 在移动，但真正符合 fixed first law 的是原子在移动，不要忘记哦。这个给大家做。那 driving force 的话，永远都是 potential 的 gradient 再加一个负号。那这里的 surface energy 跟 average atomic volume 都是常数，会随着不同曲面跟材料而改变，所以这里能做 gradient 的只有kappa，所以这里就会是 kappa 的 gradient。OK，那如果有人硬要写 vacancy 的话，就会是相反方向，所以这给大家做参考。但还是想提醒一下大家，不要忘记在材料里面真正主动移动的只有原子，vacancy 其实不会移动的，可以吗？Okay, I'm going to give you an examples regarding to the narrow scale Kirkendall effect. Some scientists use this effect to synthesize hollow narrow particles or hollow narrow tubes, as we mentioned in prior slide. But we will put more efforts on or put more focus on the synthesis process step by step. So what we have in the beginning is we have the core as material A and share as material B, and we try to heat these materials up. So usually the temperature will increase up to like zero point 0.7 of a melting point to allow interdiffusions happen between this A and B. So my question would be, what will be next when I try to heat these materials up? What happened as a function of time, especially for the morphology evolution? So probably at this moment, you need to think about that. When you try to heat these materials up, how many possible driving force acting on these kosher materials? So possible driving force. So probably you can list the 4 possible driving force you have learned in this lecture 2. The first one is, do we have a chemical potential gradient? Do we have? Yes, right? Because you have A here and B here, and the concentration is different, and also the concentration distribution is different. So which demonstrate that this material is in homogeneous chemical matrix. Okay, so we do have chemical potential gradient, or you can consider as concentration gradient. But here we did not apply the battery, or so we don't have electrical potential gradient, EM, or this material is maintained at constant temperature, so we don't have temperature gradient as well. And regarding to a curvature gradient, because this is not a hollow structure, not a hollow structure, it's a solid narrow particle. So the curvature we only have one curvature, which is the reciprocal of R radius. So the only possible driving force here is chemical potential gradient. So as long as this chemical potential gradient serving as a driving force, then you can try to figure out if this serve as a driving force, what happened next. So at this moment, you will image that the interdiffusion will be happen, right? Because A tend to move to somewhere where with lower chemical potential will be go out. So that will induce the flux. So if you're for your material design, if you design JA larger than JB, then in order to reach net flux equals to 0 at any specific plane inside my materials, so that will come out a vacancy flux move inward. So due to this vacancy flux, we will observe some vacancy in material A. As time increase, you will get more vacancy, and this vacancy probably will accumulate to form what form some void. Okay, okay. So sorry. So probably I can use a blue one. Okay. I will observe some vacancy. As long as you have lots of vacancy, then it probably will accumulate together to form some void in material A. So this is what we call it as a Kirkendall effect, but happen in narrow scale particle. So we call it narrow scale Kirkendall effect. And you will have the interdiffusion in between A and B, right? So you will have form some AB alloy outer in the outer region of this narrow particle. Okay, so let's try to answer questions. So Kirkendall effect, that will come out a vacancy flux move inward to form some void, and the outer region you will have a AB alloy, right? But as time increase, probably this void will get together to form a larger voids, right? But when this uh, kinetics or interdiffusion stops until what? Until the driving force disappear. What at what kind of condition this driving force is going to get disappear? There's no chemical potential gradient exist on these materials, right? So which means that you do not have a concentration gradient for A and B. So as long as time increase, as long as the um, your particle to form the AB alloy uniform with a uniform concentration for A and B, and at the center, all this void will form a will get together to form a big void. The most important part is the only driving force disappear when you have a uniform composition or uniform concentration for A and B. So under these situations, system will due to this driving force disappear. So system will go to the morphology revolution of this narrow particle. Narrow particle will turn out like this. We call it hollow narrow structures or hollow narrow particles. But if at this moment I still keep the temperature, I still heating these materials up, and that will what happened, and still wait. So I also want to ask about the morphology evolution as time increase. What's the next step? Because the only possible driving force chemical potential gradient disappear, and the morphology go like this. But if I try to heat these materials up, and what happened as a function as time increase? So at this moment, you need to also the same idea. You can write down the possible driving force you have learned so far. Then we don't have a chemical potential gradient anymore because we have the AB alloy, and we did not apply a battery, and the temperature for the inner or outer service will be the same, so we don't have temperature gradient. But we do have a curvature gradient because for the convex region, the kappa is positive, but for concave region, the kappa is negative. So we do have a kappa gradient exist on our materials. So at this moment, if you try to provide the heat these materials up, then kappa gradient will serve a driving force to drive this morphology evolution. Okay, so this is what we call the capillarity effect will dominate. So do you remember where how the capillarity effect induced the atomic migration? The atoms with high surface potential region, which it means that at the convex region 2的地方，那它拥有 higher surface potential，它就会 moves this atom somewhere with lower surface potential site. Usually will be the concave region, 就是凹的地方。So this is atomic point of view. So it turns out if all the atoms at the outer surface tend to move to the inner surface, then this structure will shrink. So the particle diameter will shrink as time increase. Until when? Until this driving force disappear. Okay. And the others, people probably will switch their observation point of view. They switch to like, how, Professor, how about if you switch your view as your vacancy, does this is this results correct as well? So let's move. Let's try again. This results actually we derive from previous slide here. Wait here. Just copy this results. Oh, I just use this results. This results is regarding to concentration vacancy as a function of curvature. So just directly grab these results. And because we switch to vacancy point of view, so when the kappa is positive, which this is means this is positive, exponential, you have a negative term. So which means that you have small vacancy concentration vacancy at convex region. So on the convex region, you have lower vacancy concentration. So you have a lower vacancy concentration, which you can write down small. But however, at the inner concave region, the kappa is negative. Then negative, negative, so exponential term, you have positive, so you will have large or higher concentration, vacancy concentration. So if you switch to vacancy point of view, higher vacancy concentration at the inner surface, lower concentration of vacancy at the outer surface. So the vacancy, sorry, probably I can. I can switch the, so for the vacancy, I can write down. For the vacancy, we have a higher vacancy at the inner wall and lower vacancy at outer wall. So based on the concentration vacancy, so for the vacancy point of view, vacancy is going to move from inner surface toward to outer surface. Compared to the one I just show you from the from the atoms point of view, we do have positive kappa for the atom, right? This is atom. I show them in blue. From atom point of view, the kappa is positive, so atom have higher surface potential and move to kappa, move to the inner surface with a negative kappa. So this is based on the surface potential you have learned here. And concave region, you have negative 10. Okay. Okay. So after, no matter it's based on the atom's point of view or vacancy point of view, the morphology evolution for this hollow narrow particle will go shrink, which means that the diameter of this narrow particle will decrease as a function of time until the driving force disappear. Okay,